Hello, welcome back to Engineering 211 Statics, and I wanted to pick up where we left off last time, continuing to work with vectors. And we're going to talk today about using position vectors to help better define force vectors. So if we start out talking about a position vector, we'll talk about maybe the easiest case where its origin begins at the origin of a coordinate system, or it originates at the origin of your coordinate system. It might be a better way to say that. We'll use again a right-hand coordinate system, x, y, and z. That's going to become critical when we start crossing things. And let's say that we have some point out here. We'll say that point is P, and it has an x coordinate, a y coordinate, and a z coordinate. So we could have a position vector, maybe we will call r. That's oftentimes what we use for a position vector. So position vector r, that it begins at the origin 0, 0, 0 and goes to point x, y, and z. So we could write r then, if we wanted to, as x in the I direction plus y in the j direction plus z in the k direction. Okay, now that's hopefully fairly straightforward. If we were to look at a bit more complicated system, maybe I'll come over here and draw that. Again, I'll start with a right-hand coordinate system. Y and z and x out here, and I'll put a point out here. Maybe I'll say that this is A, and it's going to have some x, y, and z. And then I'll put a point out here. Let's call this B, that will likewise have some x, y, and z. Maybe we'll say eventually that's B sub x and excuse me, x sub b and y sub b, and so forth. So let me define some position vectors starting at the origin here and going to point B. I'm going to say that I have r sub b, and starting at the origin and going to A, I'm going to have r sub a, and then going from point A to B, I'm going to have r. So if I were to look at this in a vector sense, adding those vectors tip to tail, I could say that I have r sub a plus r is equal to r sub b. That is, going from there plus that is equal to r sub b. That's simple vector addition. So I could rearrange this and say then that r, the vector r, is equal to r sub b minus r sub a. And if I make the substitution for what r, b, and r a is, I could say then that r was equal to, let's say, x sub b in the I direction plus y sub b in the j direction plus z sub b in the k direction. And then I need to take that and I need to subtract off x sub a in the I direction plus y sub a in the j direction plus z sub a in the k direction. Sure I've got those right, a's and b's, yep. So if I go through and group the i's and the j's and k's, I could say that this position vector r is equal to x sub b minus x sub a in the I direction plus y sub b minus y sub a in the j direction plus z sub b minus z sub a in the k direction. And you see then fairly quickly it's the end minus the beginning. Our r vector is defined as going from A to B, so we take the B coordinates, the end, its destination, and we subtract the starting spot, or the starting coordinates, or where it originates from. So hopefully fairly straightforward. And again, that makes sense when you look at the starting point here of 0, 0, and 0. If you take this point P and subtract 0, 0, 0, you come up with this. So hopefully that's consistent. Now what we're going to do with the position vector is we're going to use this position vector to help us define a force vector. So let's say that we have something here, and we've applied some force to this, and I have some position vector or maybe for now I'll talk about a unit vector in some direction, I can use this unit vector, which is really equal to the position vector divided by the magnitude of the position vector. So this unit vector simply gives direction. So if you could come along and you could find a position vector that maybe goes from there to there, defining that position vector and dividing by the magnitude of that position vector, you get this direction then that will define the force F. So if we know a couple points along the line where this F is acting, or maybe even a point out here, we can define the position vector and use that position vector to define the unit vector. We can say then that the force vector F is equal to its magnitude times the unit vector. We've seen that before, which then when we substitute this in, we could say it's equal to the magnitude of that force vector times the position vector in the same direction divided by the magnitude of said position vector. So this is hopefully fairly straightforward. Hopefully you're talking about similar things in your Math 254, your vector calculus class. Probably the best way to get a good solid understanding of this is to tackle some examples. So let's see if we can do that. So I've got an example here where, again, I use a right-hand coordinate system, and I keep stressing that. It doesn't technically matter now, but when we get into the cross product, it's going to be very important. But you take your right hand, put your fingers in the direction of X, rotate them to Y, and your thumb has to point in the positive Z. So this is a right-hand coordinate system. Well, let's say that we've got this force. We've got some sort of a column or pole here, maybe as simple as a fence post or something, and we're applying a force to the top of that goes back to the origin. So the top of this is point A, the origin down here is at B, and that force is going from A to B. And we're told, we're given then, given not only this figure, but we're given that the force in vector form is minus 120 in the I direction, minus 90 in the J direction, minus 80 in the K direction, and that is in pounds. So minus 120, minus 90, minus 80. And we're told then that the distance from A to B, that distance along there, is equal to 34 feet. Okay, so we're given some kind of odd quantities there, but what we'd like to do with that is we'd like to find the distances X, Y, and Z. Probably a little more common to know what the distance X is here, to know what the distance Y is here, and to know what the height of that pole above the XY plane is. But just bear with me. Let's say that we were given this information and we wanted to work backwards to get those. This will help with our understanding of this. Well, given this information, we know really that let me clearly indicate this is given. So if I work on the solution of this, I think this is page 2. So the solution of this, we recognize that the magnitude of R, which we could really just write as R, is equal to this distance AB. That'd be that 34, wouldn't it? Okay, 34 feet. So that's one little piece of the puzzle. And we know that we know what F is. We've got that. That's minus 120 in the I, minus 90 in the J, minus 80 in the K pounds. And because we know what F is, we know the magnitude of F, which I could really just write as F without the vector over it. That's going to be the square root of minus 120 squared. We wouldn't necessarily have to put the minus in there because it'll go away, plus a minus 90 squared, plus a minus 80 squared. When you do that, go through all the math, you come up with 170 pounds. Okay, so that's the magnitude of that. So let's go look at the equation here and see what we have. We know from this our previous work, this equation that we developed here, that F is equal to the magnitude of F times the position vector divided by the magnitude of that position vector. So what do we have? We have this piece here. We have this piece here. We have that piece there. So we know all but one of those quantities. We should be able to work it back out, shouldn't we? So let's go ahead and substitute those pieces in. These are check marks. They're not some odd vector notation. Just checking that I know, which is a good way to solve problems. To put an equation and try and figure all the pieces out, we know everything but one piece. We should be able to solve for that remaining piece. So let me make that substitution. We have minus 120 in the I direction, minus 90 in the J direction, minus 80 in the K direction is equal to, then, what do we get for the magnitude of F? 170 divided by the magnitude of R is 34. And then we have this R vector there. So when we solve this, we're just effectively going to take this vector and multiply each term by 34 and divide by 170. So R turns out to be minus 24 in the I direction, minus 18 in the J direction, minus 16 in the K direction. And if we go through units on this, this should have distance of, if this 34 is in feet, because this would have units of pounds, this would be in pounds, so the 34 would give this the units of feet. Now, the position vector, this R position vector, is in the same direction as F. So R is running from A to B. So from A to B, it should not surprise us that these are all negative pieces. Now we'd like X, Y, and Z, so we'll go ahead and look at the positive pieces, or say that X is equal to 24 feet, that Y is equal to 18 feet, and that Z is equal to 16 feet. And that would be our answer then. As we, before we run off from this problem, does that seem reasonable? It seems reasonable. I mean, our magnitude is, that total distance is 34, so we would not expect any of those to be greater than 34. Looking at the relative direction of this, it should not surprise us that the position vector is negative because it's going from A to B. So stepping back and making some of those checks, doing what I call being more concerned about being approximately right than precisely wrong, spending more time to the left of the decimal place than to the right of the decimal place, I think our answer makes sense. Well, let's try another problem then. A little trickier problem, but a more real-life problem. So what we've got here is some sort of a chandelier, or maybe a pot rack or something in a big kitchen. It's got a radius of 4 feet, so it'd have a diameter of 8 feet. So it's a pretty good-sized thing. You could imagine that maybe there's light fixtures hanging from here, or maybe pots and pans hanging from here. Whatever you want, however you want to think about this. So this is hanging up, and it has then 3 cables or chains that go up and attach it presumably to a ceiling or something. So at point A there's a cable that goes up, at point B there's a cable that goes up, and at point C there's a cable that goes up. And there would be 3 forces acting down those cables to support this. Those cables would then be pulling on this joint up there, trying to pull that down away from the ceiling. So this geometry is a little tricky. These are spaced evenly on this circle. So if we look in the XY plane, we'd have something like this. Point C over here is on the Y-axis. Point A is over here 30 degrees from the X-axis. And point B is 30 degrees from the negative X-axis. So if we look at this as a right angle, you take 90 and 30, you get 120. So our total angle here is 120. This balance in here is 60, so along with this, so 60 and 60 is 120, and then again 90 plus 30 gives you 120. So those are all 120 out from each other. So given this, and the fact that the magnitude of force A is equal to the magnitude of force B is equal to the magnitude of force C is all 60 pounds, we'd like to find each vector. Find FA, FB, and and FC in Cartesian form. And maybe to keep it interesting, and we'll find their resultant. Okay, so that's our task at hand. So we could just do this alphabetically. Probably C is a little easier. If you're in group study, you might be the hero and volunteer for C. But let's see what F sub A looks like. Remember, we're going to use the equation that force is equal to the magnitude of the force F times the position vector divided by the magnitude of the position vector. So we're told that the magnitude of F, that is 60, and then I need to come up with this position vector that goes from this point here, that's 6 feet above the ring, to this point A, which is probably a little easier to see on that figure there. So to get there, I'm going to have to go, what? 4 cosine 30 in the I direction, minus 4 sine 30 in the J direction, minus 6 in the K direction. Does that make sense? Let's see if that's right. A lot of times I'll actually just write these brackets here and fill in the pieces, not necessarily in I, J, K order, but a lot of times thinking about getting from this point down to A. How could we do it? We could go down there, which would be minus 6 in the Z direction, which would put us right here at the origin. So minus 6 in the K. And then we sit at this point there, and then how do I get to A? I'm going to have to go out 4, because that's the radius of this thing, 4 times the cosine of 30 in the X. And we're going to have to go backwards, because this is minus Y, 4 sine of 30 in the J. So I think that's okay. Now the magnitude of this thing is going to be what? It's going to be the square root of 4 cosine 30 squared plus a minus 4 sine 30 squared plus a minus 6 squared. Okay, so that would be F sub A. You could run that through your calculator. And incidentally, as you're doing your homework problems, I think this is a reasonable amount of work to show. If you just go from this and come up with F sub A, we don't know how you got that. And if someone's grading on partial credit, our test in here will be multiple choice, so it's not necessarily an issue here, but if someone happens to be grading your homework or a test in the future in partial credit, they have a very difficult time giving you credit for what you've done if they can't see your work. So the math, when you grind through this, the math comes out as 28.8 in the I direction, minus 16.6 in the J direction, minus 50 in the K direction. And that is pounds. Okay, that's pounds. So there's F sub A. I guess we've done that one. You can do that. Well, what's F sub B look like? So F sub B is going to be, again, 60. Now times, what do we have here? We should have a lot of similar terms. This time we have minus 4 times the sine of 60. Let's see, maybe I won't write that in terms of sine of 60. Why don't I say cosine of 30? Minus 4 times the cosine of 30. Minus 4 times the, whoops, messing this up. This is in the I direction, isn't it? And then minus 4 times the, I want to say cosine of 60, but why don't I say sine of 30 in the J direction, and then minus 6 in the K direction. Let me check that out before I write the magnitude underneath it. Does that work? Again, I'm going to B, so I'm going to this point over here. So I start here and I go down the z-axis That's minus 6, so that term's okay. That puts me at the origin, and now I'm trying to get to point B. So in the x direction, I'm going to go this. Remember, this is minus x. I'm going to have to go, what, 4 cosine of 30. So there's minus 4 cosine of 30. And then in the y direction, or the minus y direction, so these would both be negative, I'm going to have this piece over here, aren't I, which is going to be 4 times the sine of 30. So you could say that this was minus 4 sine 60 and minus 4 cosine 60, but since I've got the 30 defined, I will use the cosine of 30, which is this side here. That's the x piece, and the sine of 30, which is that side there. That is the y piece. Okay, I think we're okay. So then the denominator here, the magnitude, would be 4 cosine 30 squared, and you can put the negative in there, plus a minus 4 sine 30 squared, plus a minus 6 squared, right? And actually, from the geometry, this really represents the distance from there to there. That would actually, those denominators would actually be the same. They should come out as the same number. Well, when you run the math on this, this turns out to be equal to, let's see, do I have a number for that? Yeah, there we go. Minus 28.8 in the I direction, minus 16.6 in the J direction, minus 50 in the K direction. And that would be pounds. Now, we've seen some of those before. Yeah, this is the same except it's negative. One's pointing in the positive x direction, that's A. One's in the minus x direction, that's B. The y pieces are both negative, that's good, and the z is negative. So I think our answers are looking good so far. Well, let's continue on looking at what we have for f sub c. So I'll put this up here. F sub c would be equal to the magnitude, so we're going to have 60, and then I need to come up with how to get from this point up here to c, and that's actually a little easier, isn't it? We're just going to go 0 in the x plus 4 in the j minus 6 in the k. That's why I said this is the one you might want to volunteer for if you're doing group study. Does this make sense? We get up here, we go minus 6, that takes us to there. We don't have to go any in the x, we simply go positive 4, because that's the radius of this thing, in the y. So I think we're good with that. We divide this then by the square root of 0 squared plus 4 squared plus a minus 6 squared. And I've been a little careless with those negative signs because they go away when you square that. Okay. Double check the work there. Yeah, and interestingly enough, that denominator comes out exactly the same as the other ones. So our math yields up that f sub c is equal to 33.2 in the I direction. No, there's nothing in the I. That should be what? 0 in the I, so this would be j, wouldn't it? Okay, so positive 33.2 in the j minus 50 in the k, and that would be pounds. So that'd be our answer for f sub c. So we've got f sub a, f sub b, and f sub c. Well, if I add them together, I could say that the resultant, remember we're asked for the resultant here, which is really just the sum. The resultant is going to be f sub a plus f sub b plus f sub c. So I'm going to take these three and add them together. So for the I component, I'm going to have 28.8 for f sub a minus 28.8 plus 0, so I get 0 in the I direction. Then I'm going to have minus 16.6 minus another 16.6 plus 33.2. That gives me all total 0 in the J direction. And then I have minus 50 and minus 50 and another minus 50. I'm going to have minus 150 in the K direction. So I could really just write this as minus 150 K, and that would be pounds. Now, does that make sense? Hopefully so. I mean, if we look at the sum of 60, you had 60 and 60 and 60, you get something over 150. But remember that these are larger because these are at a bit of an angle. If they were pulling straight down, then they would be 50 apiece. So I think we can rationalize that pretty well. It seems to be reasonable. If I wanted to put this in magnitude angle form, I mean, this is Cartesian form right now. If I wanted to have it in magnitude angle form, could I come up with alpha, beta, and gamma? Well, the magnitude of this is, of course, just 150 pounds. And then I could say that alpha would be what? The arc cosine of 0 over, is that right? 0 over minus 150, which gives you 90 degrees. That beta is the arc cosine of, what do we have there? 0 over minus 150, which gives you 90 degrees. And that gamma is equal to, let's see, I should have been a little more careful here. The components could carry a negative. This is going to be positive. So I'll put that in as positive because that's the magnitude of the force, which would be positive. Now with the gamma here, the cosine, inverse cosine, I'm going to have this negative here. So I'll have that minus 150 divided by 150, which is the arc cosine of minus 1, which turns out to be equal to, what, 180 degrees? Well, let's see, does that make sense? If we resolve these, we would expect it to point straight down. So if it points straight down, alpha and beta should be 90. That's true. And then remember, we're going to measure from the positive z-axis. This indeed had better be 180 degrees. So I think we're okay with that. Let me double check my trig relationship there real quick. Yes, I think we're good. Good. So these would be our alpha, beta, and gamma if you wanted to have it in magnitude and angle form. It didn't necessarily say, but I wanted to do that for a little extra practice. Well, let's see. We're going to change gears kind of significantly here and go into the dot product. Let's do that. Let's see how that works out. So hopefully you've started talking about this in math. If you haven't noticed, if you're taking math and physics and statics all at the same time, we're basically talking about exactly the same thing in all of those classes right now. We use different symbols, different terminology, but basically the same thing. So that repetition and the diversity of the perspectives makes learning this, really reinforces that, I think, which is good. Well, the motivation for the dot product is if we take a couple of vectors in space. Let's say I have vector A and I have vector B. Okay, so I've got those two vectors in space, and I can't really do them justice here on the page. You could imagine that A might be pointing into the page some and B might be pointing out of the page some. So they're really vectors in space. And I could ask a couple questions. So thinking of these in space, what is the component of A on B? That's one question that I might ask. What's the component of A on B? Or vice versa, what's the component of B on A? And then the other question is, what's the angle between them? What's the angle between them? And this seems very easy. You could lay your protractor here, but remember, these are in space. This A possibly pointing into the paper, B pointing out of the paper. That gets a little trickier. So the dot product is going to be very useful in finding both of these quantities. So let's introduce that dot product. And I can say by definition that vector A dotted with vector B is equal to magnitude A times magnitude B times the cosine of the angle between those two vectors, where that angle theta has to be between 0 and pi. Okay, if you're dealing in radians. Now, this is the dot. That's fairly standard. I will normally try and, if I have a, let's say, a couple values, when I do multiplication, I either just put them right next to each other like this, that's multiplication, or maybe I'll put parentheses around them. I usually don't use the dot for multiplication. So if I put a dot and kind of make it like a small O there, that really means the dot product. It does not mean multiplication. Well, let's then define A. Let's say that A has some x value, so we'll say x sub A in the I direction plus y sub A in the j plus z sub A in the k. And likewise, B, we can say, is x sub B in the I plus y sub B in the j plus z sub B in the k. Okay? So I can, by definition, if I dot A with B, what that is equal to is x sub A times x sub B plus y sub A times y sub B plus, and I got these x, y, z plus z sub A times z sub B. Okay? So multiply x's times the x's, y's times the y's, z's times the z's, and add them up. And the interesting thing about this is the dot product takes two vectors and it gives you just a number. It gives you a scalar. Okay, so the result of the dot product is not a vector, it is a scalar. Well, there's some rules for doing this. Maybe we should jot some of these down. What is A dotted with A? So you dot something with itself, it really just turns out to be the magnitude of that vector squared. Okay. Another rule is it's commutative. A dotted with B is the same as B dotted with A. Okay. Let's see. Another one. A dotted with B plus C is equal to A dotted with B plus A dotted with C. So it is distributive. Okay, you can distribute that back through. A dotted with B plus A dotted with C. And finally, we could say that a constant R times A that's dotted with B, towards the edge here, but I think we'll get that, okay, would be equal to R times A dotted with B. And we could go full circle on this if we wanted to and say it's equal to A dotted with R times B. So those are some rules for doing the dot product. I suspect you've already learned or will soon learn those in math. The last thing that I would like to do, so we'll say rules, is rearranging this definition because I want to come back and try and find the angle between these. If I rearrange this, I could say that theta would be equal to, rearranging this, theta would be equal to the inverse cosine, the arc cosine of the quantity vector A dotted with vector B divided by magnitude A times magnitude B. Okay, so theta would be the arc cosine of A dotted with B divided by magnitude A times magnitude B. Now this is also kind of interesting. What is A, vector A divided by its magnitude? That would be the unit vector for A, wouldn't it? So we could likewise say, and sometimes there's an advantage here, it's the arc cosine of the unit vector for A dotted with the unit vector for B. Do a little better on that B there. I'm messing that up. Okay. So because the vector A divided by its magnitude is the unit vector for A, and B divided by its magnitude is the unit vector for B, we can really say that theta is equal to the inverse cosine, the arc cosine of the unit vector for A dotted with the unit vector for B. So got quite a bit of a theory, looks like a little bit of math here, but it's set us up nicely so that we can use this to work some examples. And when we come back next time, the next lecture, we will apply that to some examples. I don't know if you've noticed as we've gone through this, we usually introduce some theory, and then we work some examples trying reinforcing that theory. And then we introduce some more theory and work some examples reinforcing that. Well, we've come to a stopping point here. We've got some theory on the table, and we'll go forward next time and use some examples on this. As we wrap this up, we'll be going ahead and starting to look at moments and systems of those. So that's where we're going. Again, thank you for watching, and take care till next time.